Hello, everyone, and welcome to today's seminar hosted by the Princeton AI Club. We are very happy today to have Dr. Naila Murray from Facebook AI Research with us. So Dr. Murray is actually a Princeton alumni, receiving her BSc from Electrical Engineering from the university in 2007. She then moved on to receive her PhD from the Universitat Autònoma de Barcelona in 2012. She joined Xerox Research Center in Europe in 2013 and is now currently at Facebook AI Research as a Senior Research Engineering Manager for the Europe, Middle East, and Asian region. Her current research interests include few-shot learning and domain adaptation, and today she will be discussing with us her recent work on training deep vision models in low data regimes. Please take it away.
Thanks so much, Penning, for the introduction, and thanks for the invitation. Happy to be here. So as Penning mentioned, I'm going to be talking today about some recent work on training deep vision models in low data regimes. So I'll describe what I mean by all of that. So let me just mute that. Right, so maybe let's start off first about talking about what's the high data regime, right? So we could call this the regime that I would think is pretty familiar to most folks working in machine learning. So it has, because this regime has a pretty successful history of leveraging large-scale data, right? So a typical paradigm we're probably all used to and familiar with is a sort of pre-training and then fine-tuning paradigm, right? So let's imagine you have some large-scale data sets. So this is sort of like where the high data regime concept comes from, such as ImageNet, which has millions of images, each of them being labeled by a human. Or in the NLP space, in the language space, having a data set such as Common Crawl, which is an unsupervised data set, right? It's just like a sort of dump of internet data. So both of these types of data sets, both of these data sets and others have been used to pre-train models, pre-train large models, and these could be pre-trained in different fashions, either in a supervised manner if you have labels, in the case of ImageNet, or using unsupervised or self-supervised methods, which have been used both for things like Common Crawl and then also for ImageNet as well. And then once you have this model, which it is assumed is a model of the type of data you're working with, either images, text, or other things, you're assuming that this model now gives you a good, let's say, robust and generalizable representation. And then you use this representation for downstream tasks, right? And so typically when you're applying these models to a downstream task, you don't apply directly. So you're going to do some sort of fine-tuning, which is usually supervised on these downstream applications. So some applications you can think of is object detection, where for those of you who may not be aware, so this is like a vision problem where you are given some sort of image or video and you want to localize and classify objects within that image or video, whatever visual content you're looking at. Or you can think of applications, for example, in the autonomous driving domain, where you might want to, once again, do detection or, for example, semantic segmentation of pixels in, for example, an urban scene, right? And then you have data sets like the Kitty benchmark suite, which is typically used to kind of train and fine-tune pre-trained models on these tasks. So you notice here I mentioned that these are typically supervised, right? So even though you're kind of not necessarily having like a ton of data now, you're still expected to have some decent amount of data, and it's still expected to be supervised data. So the thing is, so for most or many downstream applications, it's actually not that easy to collect the large amounts of labeled data that you'll need for your fine-tuning, right? So you can think of some examples. Let's say you are an e-commerce store. E-commerce stores are places where you're continuously having new content that are coming onto the store, like new catalogs, new items for purchase and things like this. And so if you want to train or if you want to apply machine learning models to this data, you're going to either have to kind of constantly be labeling new data that's coming online in order to be able to process it appropriately, or you're kind of stuck, right? So you can think of one application is, let's for example, you're using visual search. So for example, you take your camera and you take a picture of somebody wearing something that you'd like to find online. You take this picture and you try to, you send it to Google search or something like that to be able to figure out, oh, where can I buy this thing? And in order to do that, you would like to have had that information be trained, but you may not have seen that, right, at fine-tuning time. Another example you can think of is relevant to social media. For example, let's say that you have some new content moderation policy, or like some new kinds of content and the way that that content should be treated, some new rule for that. And you wanted to detect violations of that policy. And so policies can change quite a lot, and also content changes quite a lot. So this is a sort of constantly evolving space where there's a constant need for fine-tuning and adapting your models. And this is also one place where it's very hard to continually collect the amounts of label data you might need to have effective models here. So rather than taking this kind of fine-tuning approach, an alternative is to use weakly supervised methods, right? So these are methods that try to adapt models or train models to new data, typically out of distribution data, without requiring large amounts of supervised data. And that's the approach I'll be discussing today. So here's a quick agenda, very high level one. So I'm going to talk through 3 recent works that cover different vision problems. The first one is video action segmentation, and the second 2 will tackle few-shot object detection. And so I'll go through each of these and just describe how, in a context in which there's either very little or no supervision and very few examples, what can we do with this, basically? So let's start with the first one. So I'm assuming, not everyone here works in computer vision, so I'll just go through super briefly what the problem is we're trying to tackle. So this is a problem of action segmentation, and the task here is you're given a video, right? So a sequence of frames, and you're simply trying to temporally segment this sequence. So you want to have some potentially mostly contiguous block of video frames, and you want to assign a label to that, right? Like some sort of label of an action. So to give this example here, like you say you have like a video of somebody making hot chocolate, and that activity of making hot chocolate can be segmented into certain actions. For example, taking up a cup, putting in powder, pouring milk, etc. So we approach this fundamentally as a grouping problem. So you're basically trying to group frames, right? So this is kind of like the inductive bias we're using here. And given that, we will adopt a clustering approach, right? So this, as I mentioned, is a key inductive bias, which is that the clusters in this clustering approach, which in this case correspond to actions, should be visually and temporally coherent. And this is a bias we're taking from the fact that we know that they're video frames. So we expect that they should be not just visually coherent, but also temporally so. And we'll see that this is a bias that can lead to errors in some cases. It has its limitations, but you'll see it's also pretty powerful as well. So let's talk about the clustering. So we mentioned this is a clustering problem. So let's say we have this video with n frame representations, x1 to n. Each of these is some sort of feature representation that we will extract from some sort of arbitrary encoding. Given this, we define some directed graph G, where the vertices are the video frames and the edges encode a visuotemporal distance. So we're going to encode this distance as follows. So it's derived as a combination of visual and temporal distance graphs. And so you'll see the first one, which is the visual graph, the visual distance graph. This is GF for sort of like visual features. And what we're seeing here is we'll see the distance between a feature I and j will be low, right? So basically it will be like 1 minus the dot product between them, the inner product between them. And so therefore it'll be low if they're similar, and it'll be 1 if they're not. So these, just to be clear, each of these representations are L2 normalized. So, the maximum similarity you'll get from them is 1, which means that the maximum distance you'll get here, well, the minimum distance you'll get is 0. And then you have so these constitute the edges, right, in your visual graph. And then you have the edges from your temporal graph, which are quite simple. So it's literally just like the difference between the 2 timestamps, the absolute distance between them, normalized by the amount of frames for that given video. Right, so you kind of have these 2 separate concepts. You have visual distance, you have temporal distance, and then we combine them in a very simple way, very intuitive way, to give you the overall visual temporal distance between any 2 frames. Okay, so out of this, we compute our final graph edges, which is we convert this into sort of binary edge weights, so that, for example, for any, like if you have a frame I, it's linked to a frame j, if and only if that frame j has the minimum distance, right? So it's the closest frame to I. Otherwise, it's 1. So in this case, it's a 1 nearest neighbor graph. And in fact, we make this a symmetric graph afterwards by having the reverse be true. So ji is also 1. Ji is also 0, sorry. if this first case holds. So that's our graph. So now that we have a graph, what do we do? How do we cluster based on the graph, right? So we can start off with a set of, let's say, probably overly clustered, over-clustered graph, using simply calculating the connected components from this graph, right? So we're going to use this as sort of like a base set of clusters, and then we're going to hierarchically merge these clusters until we just have one cluster made. So it's sort of like an agglomerative hierarchical clustering method that we're using here. So I'm not going to go through, so this is the algorithm for the cluster. I'm not going to go through it in every detail. I'll just focus on the loop, which is the iterative loop I was mentioning, the hierarchical group. So what this algorithm is simply saying that we initialize with our set of connected components that we get from the initial graph that we have, the initial kind of one nearest neighbor graph. And then as long as there are at least two clusters in this, in our clustering, in our partitioning, we simply create a new graph using exactly the same way we create our initial graph, but we use where each of the vertices are no longer an individual frame. Each of the vertices is some kind of aggregated representation of the clusters that we have right now. So if we have some cluster CPI, that cluster, we generate one representation from that cluster by simply averaging them. And then we treat this as a vertex, and then we create our graph once again. And we do this iteratively until we just have one cluster left. So one thing I should mention is, so we have a hierarchy, right? So we have to decide, which layer of the hierarchy we want. And so we have a method to do this, which is basically which we kind of use an evaluation time. So actually, I think I'll touch upon it then, and exactly how do we decide which layer of the hierarchy we want to choose. Okay, so we have these clusters. We're going to choose some hierarchy of that cluster, and then we want to evaluate it, right? Because at the end of the day, this is an unsupervised method. So we don't have actual labels for them, right? So, but we do want to evaluate these clusters somehow to understand how valid they are. So to evaluate this, we use 5 different data sets, 5 different action and activity recognition data sets. I'm not going to go through the results for each of them, but this is just sort of for information. And in terms of the evaluation, how do we evaluate in this sense? We take a typical evaluation paradigm for this type of problem, for this unsupervised segmentation problem, which is that we compute a Hungarian matching between the ground truth cluster labels and the pseudo labels that we have from our method, which we call TW finch for reasons you'll see later. So in terms of the clusters, as I mentioned before, we have to choose a K. What we do is we take, for a given video, the ground truth number of activities, the ground truth number of actions for that video. And this gives us the number of clusters we expect to have, right? So we know that for a given video, we have, some number K of actions. And then we choose within the hierarchy the number of the layer of that hierarchy where we have K clusters. And if we don't have exactly K clusters, we have ways to merge clusters until we do get that.
So quick question.
So in terms of metrics, we use mainly 2 standard metrics in the literature. The first one is accuracy, which is literally just the mean accuracy of the label for each frame, averaged over a video and then averaged over all the videos for that activity. And then also because this metric it's simple, but it's not, it has limitations in the sense that, for example, if you have a video with very unbalanced actions, then it can sort of give a distorted picture of the performance. So we also use the Jacob index, which here we calculate as the intersection of a union, which gives a more, let's say, like a more nuanced picture of the performance. And for both of these metrics, higher results indicate better performance. So I'm not going to go into like a ton of results. I'll just go through a few things that I think are kind of interesting. So first, I'll compare to a few interesting baselines for this problem. So the first one is an extremely simple baseline where we take our video, we split the frames into K equal parts, where K is the number of activities, the number of actions for that video, which you can think of as a kind of temporal clustering baseline, where we only use relative timestamps of each frame. So you can think of this as if we had only used the temporal graph to do our clustering. This is what you would get, right? You basically get kind of like an equally split set of frames. And that works surprisingly well for all of the data sets that we consider. This is the data set, which we call the breakfast data set, and it's pretty representative of all the results that we have. And you can see here that for this equal split baseline, we get results that are pretty in line with recent unsupervised baselines and then even some weakly supervised baselines. So that sort of just indicates that these data sets are somewhat biased, right? In the sense that, or maybe it's a bit natural, right? But the fact that simply assuming that, there's sort of equal representation of activities in every video already gets you pretty far. The next baseline we consider are clustering baselines like k-means and Finch. So Finch is a hierarchical clustering baseline. It's basically the work that we base this on. It's a hierarchical clustering algorithm where we're considering only visual features. So we're not taking into account any temporal component. So both k-means and Finch are these clustering algorithms that only use visual features to do the clustering. And then we can see here that both of these methods also do quite well. So this also validates our intuition that clustering is a good framework in which to look at this, and also that it gives quite good performance. And so what we can see with our method is that it does compare quite well to these, which is, I guess, relatively natural, because once you can see that temporal clustering baselines give pretty decent performance, and appearance-based ones also, then you would expect that the combination would improve performance, and that's indeed what we see. So to compare to state of the art, I won't go into this too much. I'll just simply say that it does well compared to other methods. I would say though that it's not always easy to compare it to other methods, as folks have different ways of doing performing unsupervised segmentation. So one thing I'll point to is that different methods use different ways of deciding the number of clusters that should be used. In our case, we used K as the ground truth number of clusters per video. Some folks use the maximum number of actions per activity over an entire data set. So we do compare to this method as well, and then we see that we still compare quite favorably with other works. So in terms of qualitative results, give you a sense of how it works. I'll just show two representative segmentation examples from the breakfast data set. So here we're showing our ground truth. So we see that we have some video with a sequence of frames, and this video has like some quote unquote background frames, so some frames that don't correspond to any specific action. Then we have these five actions here represented by a different color. And then you can see that if you look at the two appearance-based baselines, you can see that they perform, they're really sort of over-segmented, which is kind of expected. Because they don't have any temporal consistency included. And then you see we have some other methods, some unsupervised state-of-the-art methods that perform relatively well, but have certain artifacts, whereas ours does pretty close to the ground truth. We see in the second example here, similar results. However, you can see here that in our case, we do see some over segmentation here and some mislabeled labels as well here and in a few other places. So to conclude on this part, we do see that, firstly, a clustering approach is performant for this task, and that simple appearance-based baselines are already competitive. And I would note that, here we've used no labels at quote unquote training time. We've simply used a spatial temporal clustering method. The limitations of that, though, is that it can lead to over segmentation if you have an action that's visually incoherent. So if it kind of looks like the visual coherence is not consistent, then you may over segment that action. And then also we're assuming here temporal action contiguity. We're assuming we have like action 1, action 2, etc., which doesn't always hold. So that's kind of like the trade-off here. So that's task 1. Maybe I'll stop here just to say, if anybody has any questions, feel free to put up your hand, or at least, actually, I can't see people's hands when they put it up, but maybe somebody can. But just feel free to stop me somehow if you have a question. Oh, I see a hand.
Yeah, so I have a
Cannot hear you though.
Oh, can you hear me now?
Oh, sorry. Can you say that again?
Can you hear me now?
Yep, I was on mute. Sorry, I was muting you.
That's okay. I have a question about like you said that you can like if you choose like shorter intervals of time, you may have like over like too many segments. So can you also learn like the segments like what's because like in a way every task should have like different segments and different interval of times of how much time each task takes. So can you also learn these parameter as well?
So we probably could. The thing is, so remember, we're using an unsupervised method here. So we actually don't do any learning, right? So what we do have is, I guess you can call it some kind of prior or side information. So we're using, the information we're using is the number of actions we expect in a video. And we have that on a per video level, which can be reasonable in some cases and not in others, right? So in that case, I don't think there's like a ton they can do. But if you want to trade off a little bit in terms of using kind of more side information or using more supervision, then yes, I think you could gain there.
Okay, thank you.
Thanks. Okay, I don't see any other hands up, so I'll move on, but stop me if I'm missing somebody. So let's go to the next, this is why I was muting. So let's go to the next task, which is few-shot object detection. So once again, to introduce this problem, I just keep track of the time. So object detection, for those of you who aren't aware, is the task in Vision of being given some sort of image, right? Like we're calling it, in this case, a query image, and then detecting the presence of one of some set of classes of interest, right? So you may have, for example, 20 classes, and you want to detect whether one or more of them is in the image, and also to localize those instances, right? So just to give the example for one class of interest, let's imagine we were only interested in whether there was a dog in an image, then you would input this image, and then you would have some sort of network that would be able to give you the location of the dog and then also to label it and say, okay, this was a dog. Okay, so that's the object detection part. The few shot part is we want to be able to do this if we have just a few training samples or quote unquote shots. And typically in this setup, we are thinking of 1 to 10, so very few samples. Note though that these are labeled samples. So this is not like a unsupervised case. This is a sort of a weakly supervised case, you would say here. So that we're saying we have kind of like 1 to 10 images and accompanying labels for those images. So a common paradigm for this, a common paradigm that's pretty typical recently, is that we take some pre-trained model. So this could be a model that was trained on ImageNet and then maybe MS Coco. Then you at training time, you kind of adapt it to, in sort of like a meta-learning way, using a set of L-way Z-shot episodes. So each of these episodes contains Z shots. So for example, 5 shots if Z equals 5 of L different classes, right? So you take your training set, you sample from it L classes. That could be, for example, 10 classes. And then what you have is you have some set of support images and support regions with 5 of these support regions for each of the L classes, okay? And then so the episode consists of these support regions. So these support regions, what you can call your few shots that you're going to be able to learn from. And then each episode also contains some query image. So this is the image that you're going to kind of sort of test on, right? To be able to detect. You're going to detect objects in that image. So given these episodes, you're going to compute and train feature maps. So we're going to have, for example, a feature map, one feature map phi star, representing the feature map for the query, and then some set of feature maps phi for the support regions. We also call them kind of bounding boxes. So you see support BB down here. So you take these feature maps, well, you compute them using some kind of network. This could be like a convolutional network or some other kind of network, a visual transformer or sort of anything. Well, maybe, yeah, you can say a visual transformer as well. And then once you have these encodings, you sort of compare the similarity, like you compare them somehow, right? You compute some sort of similarity between them, and then you use the similarity to predict an output and a location of any existing classes in the image. So you can see that, computing the similarity, basically comparing these two, right? This is kind of there's a real notion here of using kind of, you can say, prototypes of a class, right? Like these sort of few shots that you have, and then using some query and then comparing them, right? Computing some similarity. So the similarity is really like the core of this type of paradigm. And so the question, you can ask a good question, which is, how do you compute the similarities? Like you can find quite a few options. The first one you can think of is simply computing the inner product between some vectorial representation of your support regions and your query images, or maybe like your query feature map. That has like pros, right? It's like you don't need any new features, which is quite important in a few-shot learning case, because it's going to be very hard for you to learn anything, right? If you just have like 50 examples, for example, for a given episode, you're not going to be able to do much. So you can't throw in like a new MLP there. You're not going to be able to learn anything very useful. So that has a nice advantage. You simply compute the inner product. However, it's pretty simplistic, right? You would want to be able to have a more performant, a more, let's say, enriched similarity than that. So of course you can go the other way around, which is what I was mentioning before, which is where you can compute the inner product of vectors, which are the output of some kind of learned nonlinear function, example like an MLP plus nonlinearity. And that, as you can imagine, has like the opposite benefits, right? So it's expressive, so your similarity metric can potentially be more discriminative. However, there's a ton of new features to learn, and that's probably going to be difficult. So there's a third option, which is to use kernelized inner product, a kernelized inner product between features. So kernelized products give you expressivity, increased expressivity, because kernel methods can they're mapping you into some very high dimensional space, potentially infinite dimensional space. And so you can learn you can achieve like pretty discriminated features from that. And the good thing is that there are pretty much no new features or parameters to learn, which is a good benefit of this method. So in this approach, we're going to kind of combine all of those for different reasons. And notably, we're going to be including nonlinear kernels, and we're going to look at two of them. We're going to look at the RBF kernel, which allows us to control some smoothness properties of the representation of the similarities. And then also we're going to look at the polynomial kernel, specifically the quadratic kernel, which is going to capture pairwise similarities between features. This introduces some sort of inductive bias, right? About the fact that we expect that comparing similarities between features will be discriminative for this task. And I mean, I think it's an assumption that's well justified, right? We know that these sort of higher order similarities between features are discriminative. So let's look at the full pipeline of this again. So this now is a pipeline for the method where I've introduced what we call a kernelized few-shot object detection method. And so what we have here is, once again, some encoding network, which gives us some feature maps. So these are spatial feature maps. So it's a 3-dimensional tensor where we have a channel dimension, so some feature dimension, and then we have 2 spatial dimensions, which are kind of analogous to, let's say, like the width and the height of your input image regions. We have here two types of feature maps per image region, and that's simply one that's higher resolution, one that's lower resolution. So we have a kind of multi-resolution representation. Then we input these representations to some kind of kernelization block, which is going to compute higher dimensional, let's say, kernelized representations, and is also going to give us bounding boxes, potential bounding boxes, I should say. So what it's going to do basically is going to take the query image, and it's going to give a list of sort of candidate bounding boxes where objects might be. And then out of this block, you're going to get some set of representations for some sort of representations, like feature maps for your image regions, and then also these kernelized representations for them as well. And then you're going to have what we call a multi-head relation network, which is going to compare the two of them in order to give you your predicted outputs. So I'll just go into them briefly, each one. So the encoding network I won't go into like a ton of detail. I'll kind of just keep it to what's necessary. So this is basically extracting feature maps from ResNet 50. So ResNet 50 is a convolutional network that as the layers with 50 layers, and as you go deeper into the network, you increase the number of features of channel, the dimensionality of your channels, and then you decrease the resolution. All right, so we use this to extract multi-resolution features, and from this we compute a set of representations. Well, let's say one representation, one feature map per, well, I should say like the average feature map for some class. So let's say here you have a support box. Let's say you're using a 5-shot case, which means you have 5 support images, 5 support regions. What you're going to do is you're going to compute like a set of feature maps, 5 feature maps, and you're going to average them across. So you're going to end up with just one feature map that corresponds to these 5. And then you're going to have a feature map for your query image. So that's the encoding network. The output of the encoding network, these 3-dimensional tensors, also can also be set as these feature maps. And then the input into the kernelization block, which is where we use these the kernels that I mentioned before. So first I'm going to look at what we call the KA, or the kernelized autocorrelation unit. So this is a unit that's going to actually be computing kernelized representations. And you see they kind of show up in 2 different places. They show up in the point before we are going to compute region proposals. And then they also show up in the point where we are going to kind of normalize them and just pass them on directly to the next block. And so how do we compute this? So what we're doing here with this unit, with these same unit here, is we're going to use that to compute our KSHS, or reproducing kernel Hilbert space kernels, and kernelized autocorrelation matrices for any of the input feature maps that we have, right? So this is going to take, so what you're going to have at the output of this is some kernel matrix, some matrix, right? A K by K matrix, where K is the channel dimension, right? So it's like so you have like a feature map with K channels, and your output matrix is going to be a K by K matrix. And each element of that matrix, so this is, for example, Kij, is going to be computed in one of either 2 ways. So you're going to have Kij, where you're computing the outer product. Basically, you can consider it to be the outer product between 2 of the vectors, 2 of the feature vectors within your feature map. And then afterwards, you're going to compute a nonlinearity over that. You're going to sum over all of the features you have, and then compute a nonlinearity, which would be the kernel function. Or you can do it sort of the other way around, which is a kernelized autocorrelation, where you apply the nonlinearity before the sum, right? So you have some case where you apply a nonlinearity to a sum, and then you apply a sum to a nonlinearity over a nonlinearity. And so these are 2 different types of kernelized representations we will use, and they have different properties, each of them. So the output of this, so once we compute these matrices, we're going to end up with 5 matrices. We're going to end up with a linear matrix, a linearized matrix. Then we're going to have 2 versions of a polynomial and an RBF, right? So we have one that's computed as an RKHS kernel, and one that's computed as an autocorrelation matrix. So basically, at the input of this, you're going to have some feature map, and at the output, you're going to have 5 different matrices. So once we have these matrices, which are encoding this sort of high dimensional information, as you notice now, we have introduced no new weights, right? So we're gaining some discrimination, right? Some discriminability in the features without having introduced any new weights, which is what we want, given that we don't have a ton of data to learn weights with. And once we have that, we're going to do some decorrelation, which I won't go into in the interest of time, but we have performed some decorrelation and also some normalization, which allows us basically to normalize these representations. I think we can summarize it that way. And one thing to note is that we do have some kind of hyperparameters here, which we learn using an MLP. So this is one place where you see an MLP, but it's quite a small one. And then the last thing I'll mention is the attention region proposal network. So for those of you who are familiar with like object detection, you'll know that region proposal networks are quite a standard part of this. This is basically a network that takes in some feature map and outputs a set of candidate regions where objects might be, right? And so there's an attention version of that, which uses attention between two sets of features, and in this case, support features and query features, in order to improve the kinds of proposals that this outputs. And in our case, we use a simple attention regional proposal network, but our inputs to this are our kind of original feature maps that came out of ResNet, and then these feature maps that the kind of kernelized representations that we've just computed. And lastly, the last part of the pipeline is a multi-head relation net. So this is, I won't go into a ton of detail. I'll simply say that what this does is it takes in the feature maps, our sort of original feature maps from ResNet, and our pooled kernelized features that we were just discussing. And then we compute from them. We can kind of combine and compare each of these, either after average pooling, so using some sort of global representation, so computing a kind of overall global similarity between the features, or we can kind of combine the support and query features before average pooling them. So in that case, we kind of maintain and use some of the localized information. And then lastly, we use our patch head, which simply applies a convolutional net to our original ResNet features and uses that to regress to the actual fine bounding boxes that we're going to predict. So just to kind of refresh the memory of the whole pipeline. So once again, we have these support regions and a query image. We encode them using some network, in our case, the ResNet network. We take multi-resolution features. We compute kernelized representations of these, and we use them for two things. So we use them to compute region proposals using the attention RPN network, and then we also use them. We pass them through to the multi-head relation network, and then the output of this is directly some predicted classes and bounding box coordinates. So let's go to the experiments to kind of evaluate this. We conduct experiments on Pascal, VOC 2007 and 2012, as well as MS Coco. I won't show you results for all of them, but just a few representative ones. And we presented the metrics you see here. And so I'll simply say here on the right that we can see that our methods perform favorably to recent work. And then I think perhaps more interestingly, just to show, this is just showing it's showing the kind of the relative contributions of different kernels that we've used. So I'll just spend a couple minutes on this because I think it's interesting. So you can see that there are several options, right? We can, for example, use only linear kernels. We can use RBF kernels, either the RKHS kernels or the autocorrelation matrices. We can do the same thing for the polynomial kernel. We can use pairs of kernels. We can use all of them. We have different options. So what we've done is we've tried to combine different ones to see which combinations make sense. And what's important is that at all times, we maintain the same number of features at the output of this. So that's important because, of course, if we're increasing the number of features at the output, it's kind of hard to compare which one, what's actually happening. Is it that things are performing better because you have a higher dimensional feature representation or something else? So what we do, for example, is if we want to use two kernels, let's say we wanted to use two types of RBF kernels, two types of RBF-based representations, I should say. Then what we would do is we would take our input dimensionality, which is 1024, and we divide it by 2. And then we'd apply one kernel type to the 512 and then one to the other 12. So we always sort of divide them in that way, so that in the end we're only using and we're only keeping the same dimensionality. And so what you can see, just to summarize the table, you can see that they're all complementary. So RBF kernels perform quite well; they perform the best. Linear kernels perform the worst, but some combination of them performs quite well. So that takes us to the third work, which is, you'll see, is a fair continuation of the previous one. So here we're going to be once again doing few-shot object detection, this time using higher order tensors. So the previous work uses kernelized representations in order to increase discriminativeness. And also uses second order pooling, which I didn't talk about, but you'll see it a bit more here now, to avoid information loss. This work takes these things a bit further in terms of using, for example, a transformer architecture that can capture multi-way feature co-occurrences. So, for example, if you go back and you think about the polynomial kernel we used before, those capture pairwise co-occurrences. And so we're going to see a method here that captures multi-feature, like beyond two types of features. It's going to capture current co-occurrences of those. And then also we're going to go beyond second order pooling with higher order tensor descriptors. So the full pipeline you can see is a bit similar to what we were seeing before. So you have some sort of encoding, you have some unit that is going to extract region proposals, and it's also going to compute, let's say, more discriminative representations than the one we have here. And we're going to use those discriminative representations both in terms of producing region proposals, then also we're going to pass them through to the kind of similarity head, which we call the relation head. So I'm going to go into a bit more detail on some of these points. So just one thing to say, the encoding network is pretty much the same as the previous one. Just this time we decided not to use multi-resolution features, so we just have one resolution. And so here we kind of get to the meat of the work. So I'll spend some time on this. So here are the representation that we're using. So these are, you can consider this a kind of the analog of the kernelized features I was mentioning earlier. So here, let's imagine you want to compare two sets of features. So you can think of these as comparing two different feature maps. Okay. So one way you can do this is to use some sum of polynomial kernels as linearization. You can use some sum of polynomial kernels that you see here, where basically you're kind of, this is like an rth order polynomial kernel between these two features. And then if you sort of add it up over each of the feature pairs, right, you can get some similarity between these two sets of features, right? So that's kind of one kernel. And what you can do with this is you can, from this you can compute a tensor feature map. So this is a feature map that's going to take in some set of features, right? Your set of features phi, and it's going to output for you some representation of those features, which will be equivalent to this summation here. Okay, so this will be some sort of inner product between these two representations, these two higher order representations here. Okay, and so in this case, this representation here is going to be a tensor, and it's going to be a tensor of order n, which is generated by the rth order outer product of x. So what this basically is, right, is this is a tensor that computes multi-way occurrences of different features in your feature vector, right? So for example, you have this D, you have D like a channel of size D, right? So D dimensions for your features. And you see that this feature map is a tensor of dimensionality D to the power of R, right? So D times D, R times. And so what this is going to do is it's going to be a very rich representation. It's going to be able to capture very rich, let's say, relationships between all the D dimensions of your feature vector. Practically speaking, we use our only 2, 3, and 4. So we use second order, third order, and fourth order tensors in our work. So this, just to recap, right? So this here is this tensor. It's computed very simply using outer products, right? Like some sort of rth order outer product of your feature vectors. And what you're going to get is this tensor, and it's going to be pretty high dimensional, right? Which is in some sense what we want, right? Because we want to be able to have a very discriminative representation without having any new features or weights, right? Or parameters, as you see here. On the other hand, it can be very high dimensional, right? You can imagine if this is what we're talking about here. So we would want to reduce that size. So what we do is we kind of diagonalize this tensor and also normalize it at the same time. So we do a kind of pooling, which I kind of went through rather quickly in the previous slides, but I'll just suffice it to say that we do some sort of normalization, and then we kind of extract the super diagonal from this very large tensor. And what this does is it gives you go from having a representation that's D to the power of R to a representation that's size D. So you actually end up right back where you started, but with a more powerful representation. So that's kind of the higher order pooled representations. So now I'm just going to briefly mention the attention, how we use this to compute an attention-based region proposal network. So relatively pretty simple, right? We just compute the cross attention between our set of support representations, which are these higher order representations, and the original ResNet-based feature maps from our query image. And I think that's pretty much covers it. So based on that, we get some attention map, and then we use that attention map as inputs to our RPN in order to compute more accurate, or let's say like more effective region proposals. I think I'll skip this slide. I think maybe the only interesting thing that's important to say here is we've computed these regions, right? So we have region proposals. We have these performant representations, these higher order pooled representations for these bounding boxes. And I would simply say here at this point that we use some attention-based methods. Well, let's say some transformer-based methods as well, because we use multiple layers at times. And then we use that to compute cross-attention between query representations and support representations, as well as some self-attention methods in order to compute similarities between support features and query features. And then as an output of that, we predict directly the location and the class. So just to kind of remind once again, we take in our support images and our query images, we extract some feature maps, we extract higher order representations of these features, and we use that both to compute better region proposals and also as input into our relational unit. And then from this relational unit, we compute some cross-attention and self-attention for the final prediction, to predict the locations and the classes of objects present in the image. So once again, we use similar data sets and metrics here as in our previous work. And we show that we have results that are competitive with the state of the art. And then once again, I'll kind of focus maybe on some ablations with respect to the higher order pooled representations that we spent some time talking about. So here we see the order of the tensor, the tensor representation that we use. So we can either have second order, third order, or fourth order representations. And we can sort of combine them as well. We can combine them by, for example, splitting the dimensions as I mentioned previously. So we always kind of have a constant number of dimensions. And I'll just sort of suffice it to say that we see that all of these dimensionalities perform some boosts with certain configurations. So we can say that going to higher order representations really does improve performance. And once again, this is without having to introduce any new parameters. So to conclude on sort of this section with respect to object detection, we can see that both of them use inductive biases to generate highly discriminative representations. In the case of kernelized few-shot object detection, we're using kernels that can, for example, control the smoothness of your solution or compare feature pairs, or we're using our previous method, our let's say like subsequent method tenet, which uses higher order polynomial kernels to compare more complex feature co-occurrences. But like critically in both cases, we're gaining increased discriminativeness without having to increase the number of weights, which is crucial, of course, in our few-shot learning scenario. And with that, that's it. I'll just kind of refresh, we talked about action segmentation in an unsupervised case where we're using the notion of visuotemporal consistency to, go pretty far with no labels. And then of course we had our object detection cases where we looked at how can we increase how can we increase performance by having discriminative representations that don't need additional parameters. And that's it. Now I'm happy to take any questions.
All right, let's all give Dr. Murray I guess, virtual round of applause. And yeah, the floor is open for questions if anybody has anything they would like to ask. Okay, so I guess I have a bit of a general question. So with regards to all of these methods that you've discussed, is there anything in particular to them that makes it specific for like few shot training? Is it that like that perhaps we can also adapt these methods to the cases where we actually do have a lot of training data? Or I guess in those cases, perhaps is it because it's more computationally expensive to do these methods, and we have more data, it's not necessary to use them. We can just use a simpler representation and still get the same amount of predictive power.
Yeah, I would say so. So they tend to be sort of the typical drawback you hear with kernelized representations or representations that use kernels or higher order representations is that indeed they're computationally expensive. So I didn't go into some methods we have to reduce that, but even with the reductions, they're still generally going to be a bit slower than typical cases. So this is kind of the trade-off you're going to make. So if you can afford to have more labeled data, then you're probably going to go that way. I mean, you kind of have to really compare the two scenarios to understand, what the trade-off is like. But you will most likely find yourself in a situation where, with more data, you can kind of get away with having simpler features. Yeah, that's a good question.
So I guess there's a question in the chat from Ilya. So she's asking, would there be more human-like similarity metrics that further improve performance of these methods?
So the thing is, that's a good question. When we think of similarity here, we're thinking of similarity in the feature space. So I think some human judgment of that will be quite difficult because you're dealing with like 1,000-dimensional feature vectors and trying to see if they're similar or not. So I think that would be kind of hard to pull off with like a human-based metric. Another thing is that what we're trying to do really is avoid having humans in the loop in this case. So if we had human time to use here, I would probably use it to kind of label some data.
Actually, related to that, I had a question kind of earlier on in the presentation. We were discussing the video segmentation. So I think there you maybe this is standard in the field and just not in the field, but there you mentioned that you had these ground truth segmentations. Are those just human given segmentations of the video?
Yeah, that's exactly what they are. Yeah.
And so basically the method kind of just even approaches a kind of like a human intuitive segmentation of the video. I guess perhaps for these videos, it's kind of in a sense human obvious way of how to segment the videos as opposed to.
Yeah, like that's it's a good question because it's a bit subtle, right? Like how do the ground truth how does it come into play in an unsupervised action segmentation case? And what I would say is that it really comes into place only in terms of getting some kind of quantitative evaluation of the clustering, right? So the only way we're going to be able to say, okay, is this clustering really good, is to kind of compare it to the kind of like ground truth like labels and basically say, okay, how well do they do? And then also try to have some matching between the clusters we have and the clusters that are kind of ground truth clusters. So what we do is we take like a video, we take all the frames of that video that have a given action label, we compute representations for that, we average those representations. So we have one representation per action for a video, and then we basically compute some kind of similarity matrix between our predicted clusters and the ground truth clusters. And then we use a sort of combinatorial optimization technique to assign one predicted cluster to one ground truth cluster. And then this gives us some kind of labeling, which we then use to basically tell us how good our method is. But that's only going to be done in kind of evaluation time. It's not something that we look at training.
I see. Well, I guess if there are no further questions, that will conclude our seminar for today. Thanks again for Dr. Murray for giving us this very interesting presentation of her recent work.
Yeah, thanks everyone. Thanks, Pending, and thanks everyone for your questions and for attending.
Right. Goodbye.